Hoy tenemos el placer de tener aquí a la investigadora Zuzana Dvořáková del Instituto de Termomecánica de la Academia de Ciencias de la República Checa. Bueno, Zuzana estudió ingeniería matemática y modelización matemática en la Universidad Politécnica de Checa en Praga, y luego tiene un máster también en ingeniería matemática y modelización matemática. Digamos que su investigación la hace en el departamento de sólidos, de impactos, de ondas en sólidos, ¿no? En el Instituto de Termodinámica de la Academia de Ciencias de la República Checa. Y bueno, ahora voy a pasar en inglés.
Well, Zuzana is now going to give a talk about a very interesting topic because he's working with material defectoscopy and how to treat the data of defects in materials from the point of view of mathematics and statistics. So, Zuzana, please, you can start the talk.
Thank you, Domingo, for introduction. So, good morning, or it's afternoon, so good afternoon to everybody here, and also to students online. I am working at the Institute of Thermomechanics, and I also collaborate with the Department of Mathematics at the Czech Technical University with Dr. Václav Kus. He is interested in informational divergence, so I try to combine theoretical mathematics and application, because at the Institute of Thermomechanics we are mainly working with materials that we can use in practice. So today I would like to talk about informational divergence and their application in material defectoscopy. Okay, doesn't work. Right? Maybe.
Maybe you unplug the screen and plug it again.
Yes, thank you. Okay, so what I will talk about. Firstly, I will talk about how to use information divergence in the acoustic emission classification. So first, I will say you something. What is the acoustic emission? Which signal parameters we have used for classification of acoustic emission, how we use phi divergence as a signal parameter, and when I will talk about phi divergence, I will mention some theory about phi divergence concerning robustness of phi divergence, and I will show you some computer simulations. And then I will show you how it's possible to use phi divergence in classification algorithm. And I will show you some practical experiments on acoustic emission classification. And in the second part of my presentation, I will shortly mention the time reversal technique and how we combine it with classification and with phi divergence. And it consists, my topic will consist of questions why VTR technique is useful for us. I will show you some only basic principle because it's based on some physical theory. And then I will show you some tricks that we use on our institution. And finally, I will show you some results of combination classification of TR signals using phi divergence parameters and methods. So let's start with the first part of my presentation, acoustic emission signals classification using phi divergence. So, what is acoustic emission? You can imagine that you have some investigated specimen, some device or some material, and you have some localized source. It can be, for example, crack in the material. And when the material is under loading, the crack starts to grow, and it occurs a rapid release of energy in the material, and we can observe in material transient elastic waves. And if we put some sensors of acoustic emission on the material, we can measure these waves as acoustic emission signals. We can know that in the investigated specimen there is some crack or some source of acoustic emission. And from it follows that the main application of acoustic emission is structural health monitoring and non-destructive testing of materials. And it has various applications in industry, in aerospace, automotive, civil engineering, and for example in nuclear power plants and so on. The monitoring of acoustic emission signals consists of three main parts. Firstly, we have to detect the signals by means of sensors. We have to find the beginning of the signals, and we have to record signals. Then we have to localize where is the crack, where is the source of the acoustic emission. It's a branch of my colleagues at the Institute. And my branch is the source identification or source classification. What does it mean? Not only cracks produce acoustic emission. Acoustic emission is, you can imagine, like a sound in the materials, like a speech of the materials. So every materials produce some kind of acoustic emission. And we can measure different types of acoustic emission, and only some of the signals are coming from some cracks. And it is important to distinguish if the signals coming from cracks or if somebody is knocking on the materials or something like this. For example, if you have a nuclear reactor and you measure some signals and you can observe some acoustic emission, so you have to find out from some computation if this signals is some damage in the materials, if it is dangerous, the signals for the materials for nuclear reactor, or if it is caused by some knocking or some working in the materials, because it's really expensive to shut down nuclear reactors. So it's the classification of acoustic emission signal is a really important thing for non-destructive testing of materials. And the acoustic emission signal classification consists of two parts. We have signals, and it's almost impossible to compare whole signals because the signals. It's really long, and we measure a lot of signals. It's really time-consuming to compare whole signals. So we need some signals parameters that are typical for each type of acoustic emission in order to distinguish between types of acoustic emission. And if we have signal parameters, then we have some future space. And we need some classification methods which are able to distinguish between clusters in future space in order to reveal some groups and to say us this group are cracks, this group is only working of materials and so on. So this is my work. Here you have example of typical acoustic emission. This is so-called pen test. It's a really useful. It's really useful It's we use this test almost on every material. It's a pencil breakage on material, pen test. Yeah, and we can measure by sensors, and the signal looks like this. And we can obtain parameters directly from signals, but we often use a spectrum of the signals. And in our case, we use norm spectrum of the signals. We can see example of the spectrum, and the form of the spectrum is here, where Fs is sampling frequency of the signals. And why we use the normalized spectrum, we normalize it to 1, that the sum of the spectrum is 1 in order to obtain something like spectral density of the signals. And then we calculate some parameters from the spectrum and signals. It's not so important to go in details to these parameters. It's just example of what we do in my research, but there exist many signal parameters, standard signal parameters, but these standard parameters doesn't work very well in many applications. We will see later. But what I would like to present you how to use phi divergence as a parameter. Phi divergence here is the short definition. What is the phi divergence? For generative divergence function, phi convex on interval 0, infinity, and strictly convex at 1 with the value in 1 equal to 0. We can define phi divergence between measure of probability in this form, but we measure signals digitalized, so we don't. It's not. We cannot use continuous form of this formula, and we use discrete formula in the form of sum, where we calculate a phi divergence between norm spectra of signals. And we always calculated the phi divergence between some reference norm spectrum and all other spectra. What is a reference spectrum? I mostly take the group of, for example, pen test, and I calculate non-spectra of the signals of pen test. And from this spectra, I take average of the spectra, and all other spectra of signals that I measure, I compare with this reference spectrum, and I obtain the divergence between normalized spectra and the reference spectrum. So I started to talk about phi divergence. So now a little bit about theory of robustness of phi divergence. This is a part of my work that I did with my colleague at the Czech University with lots of schools, and I try to apply it in my research. So we have defined a new type of robustness. Here are the definitions. We define so-called model robustness of data source distribution. So suppose that we have some reflexive distance of phi divergence on a set of cumulative distribution, and we say that this model robust at data source distribution if we change a little bit the theoretic distribution of the data, then the divergence between source distributions and the theoretic distribution doesn't change so much. So this is the model robust. And similarly, we define data robust. This is important for my research because always I have some distortion in measured data, some pollution or some mistakes. So for us, it's important data robustness, and the data robustness is defined for divergence D or reflexive distance, that if we change, if there is some epsilon contamination of data source distributions, the divergence between data source distributions and the theoretical distribution doesn't change so much. And the combination of the both previous robustness is model data robust, and that means that we combine both previous definition together, and we say that D is considered to be model data robust at F and G from a set of cumulative distribution. If for every delta greater than 0 there exists epsilon, small epsilon, that if we change a little bit the source distribution and the theoretic distributions, then the divergence doesn't change so much. And the last definitions is only a little bit a small change in comparison to the previous one, because here it's for all F error and G error, and now if we define it for all F error, G error from the set of cumulative distributions, we obtain so-called uniform robustness of the distance D. So what does this type of robustness mean? In other words, model robustness means that the given distance under consideration is not so much sensitive to epsilon changes of the true statistical theoretic model. And data robustness means that if we mixed a little bit our data with some epsilon portion of some error data, we doesn't change, the distance doesn't change so much. And model data robustness is combination of these two. So for our application, we mainly use so-called Hellinger divergence, and a special self-blended version of this divergence, which has this form, where beta is the parameter of blending, and we use the value of beta equal to 1/2 in order to have a symmetry in the divergence. And again, we use discrete form of the phi divergence for signals, and we again compare normalized spectrum. And we proved that our blended Hellinger divergence is data robust against epsilon contamination in the sense of the previous definition. We did also some computer simulation to reveal discrimination capability of Hellinger divergence within some semi-parametric family F, and we have generated two data from the uniform normal logarithmic Laplace Cauchy and variable distribution, and we generated the samples of about different sizes, 10, 20, 50, and so on. And after that, after generating, we forgot the source of the data, and we try to find out if the Hellinger phi divergence is able to reveal the true distributions of the data. So here is the result of the simulation. In the case of uniform generated data, the phi divergence here is denoted like phi1, is able to distinguish that these data sets coming from uniform distribution in most cases. Here it's in percentage. And if we generate data from normal distribution, we can see that phi divergence work very well. So only for samples with small sizes, there are some mistakes, but in samples with about 100 samples, it's okay. The phi divergence is able to reveal true generative distribution. If we generate logarithmic distribution, there were some mistakes for smaller data set, but for Laplace generative distribution, the Hellinger divergence doesn't work so good. There you can see that often is revealed that the data coming from normal distribution is not true, so there are lots of mistakes. And the same is for Cauchy distribution. But for viable distribution, again, it works very well. Here is a summary of the simulation results. Here in this picture, you can see again that the Hellinger divergence works very well for uniform, normal, and logarithmic distribution, and also for variable. But there are many mistakes for Laplace distribution and also for Cauchy distribution. And this plot is only dependent on the sample of on the sample sizes, so you can see that better results are for bigger samples. And we did it also for Kolmogorov and Lekan. Yeah, similar plots, and you can see that Kolmogorov works very well for viable, Cauchy, and uniform, but it doesn't work for normal, logarithmic, and Laplace. And in the case of Lekan, it works for viable and normal and logarithmic, but there are lots of mistakes for Laplace distribution. So now again to application. It's my work. It's the main topic of my work. I have talked about how to apply phi divergence as a signal parameter. Now I will show you that we use also phi divergence in classification method. We have done a so-called divergent decision tree. It's a type of classification method. On this slide, I will present the so-called unsupervised method. That means that we don't have at the beginning any training data set. We have some set of signal parameters, and there are some so-called hidden labels. We don't know the true classification. And zeta E represents the path from the root of the tree to the leaf of the tree in the algorithm. And the goal of this divergence decision tree is to maximize the mutual information between zeta C and unknown hidden labels. And it's done through the criterion function, which has this form. And again, we here apply our phi divergence. And the resulting algorithm is as follows. Firstly, we perform so-called principal component analysis if we have lots of parameters, and we for selection some attributes of parameters. Then we done k-means. I suppose that you know that is a type of classification method. And the k-means does the division in two clusters for us, and we look at the value of the criterion function, and we choose this division for which the maximal value is achieved. And for next splitting of the node, we use the node with the largest contribution to the criterion. So it's quite easy algorithm of unsupervised decision tree based on phi divergence. At our university, we have program. We have done the supervised version of the algorithm, which is more complicated, but it was used for some data sets from Formula, and it can be used when we have some training data sets. We have some data sets, and we know how to divide it into clusters. And the training data set has this form, and we have now the information about memberships of the xi to give to class omega 1 or omega 2. And the algorithm is as follows. We calculate so-called quantile histograms for each classes, omega 1 and omega 2, for each set of k attributes. And we try to find out which combination of k attributes is the best, and we found out by the Rayleigh divergence. We try to find where is the maximum of the Rayleigh divergence concerning all k combinations from the attributes. And for selected set of k attributes, we calculated so-called kernel density estimate for both classes, and then we estimate a posterior probability by means of Bayesian theorem. And final step of this algorithm is to determine so-called division decision point delta, which is done by following decision rule, and it's done by Rhodes curve and Young index. And for each data point x, we obtain at the end the total score, which is a sum of the probability, and final classification is again done by Rhodes curves. So it was just, I don't want to go more in detail because it's too complicated to explain it in a few minutes. So it's just for some information about this new classification method. And now I can show you some experiments, but I think I will show only one. Maybe if we will have time later, we can go back to other experiments. So I will show you, for example, I hope it works. It doesn't. Okay, so maybe I have to. Okay. So, thank you. So, this experiment, we had a thick metal plate, it can be seen here, and we have attached some sensors of acoustic emission here, free and free, in two different distance. And here, these sensors, it's not exactly the sensor, but it can be source of acoustic emission, or we can use it for emitting some waves to the materials. And here is a scheme of the experiment. And now you can see the importance of the parameters. On the left, on the top, you can see two signal parameters. It's not necessary to explain what does it mean, the parameter W and Q, but you can see that the clusters are quite overlaid, and they are close to each other, and they are overlaid, and it's not possible to distinguish these two clusters from each other. So we have what we can do, we can choose another type of parameters, and we can see if we use another parameter, zeta c, and our divergence parameters, we obtain quite good separated clusters. And now this is a better input for classification method, because the clusters are compact and quite good separated. So we can see that the parameter divergence works very well in the experiment, and on the right side you can see how it's important to choose good classification method, because if we apply to this data set, if we apply fuzzy classification, it's an easy method for classification. You can see that this method isn't able to distinguish these two clusters. These two clusters are put together, and the method try to find another cluster in some outliers. So it's not good result for us. But if we use our divergent decision tree on this data set, we can see that this method is able to distinguish these two clusters. So phi divergence works better as a parameter here, and phi divergence works better in the classification method here. So maybe now you can go back. Thank you. Okay. And now the second part of my presentation is more physical, but I think it's very interesting, and it's about time reversal technique. And I will show you what is time reversal transfer, location, classification, and finally how we use phi divergence in this topic. So what is the time reversal technique? You can imagine that you have some source at the position R0. The source is some signals like this. And you have some receiver, some sensors at the position RA, and you measure something. You measure some signals. And the signals looks like something like this. And it's the result of convolution between the source signals and the ring function between the source and the sensors. And what we can do at the position of the sensors, we can time reverse the signal. That means that if we measure the signals like this, we measure this value as a first, and we take this value and we put it at the end, and we send back the last value as a first. We only time reverse the signals, and we send back these signals to the third position. And the question is what we will measure here. Again, we measure signals, which is the result of two convolution of the source signal and two green function. But after some calculation, we obtained that these signals is proportional to the source signals. So it's not exactly the same. Yes, if we have idle condition, it should be the same, but in practice, it's not exactly the same, but it's very, very similar. And it's good for application because we can remove some noise from the signal, some distortion of the signal only by means of time regularization of the signal. And this is here I will present you shortly one trick that we have done on at our institute. It was the experiment with flange section. It's from a real airplane, and we have two pieces. One piece like this, and another piece was little bit changed, and the changes was this in this area. And we did the pen test here, and there was a question if it is possible to measure forward propagation of the signal on one part and the backward propagation and at another piece of this material. And if the question was if the time reversal will focus again at the source position. And we find out that it's possible if we do the forward propagation on original part of material, and also the backward. So we obtain the green line. Here is the focus. It's on the source position. Here is the focus of the signals. But if for backward propagation, we change a little bit the part of materials. It works also very well. Only there is some attenuation of the focus, but the space in the space the focus is very well and it works. And the reason why we did it is when, for example, you can imagine if you have airplane and you have to find if there's some damage or some cracks, you can put the sensors in situ on the airplane, and you can measure some signals. But you can have in laboratory condition the same part of the small part of the airplane, and you can do the backward propagation in laboratory condition, and you can localize it on the specimen in laboratory condition, and you can call to the airplane. There is a problem, and the problem is probable here. You have to stop the airplane and you have to investigate it. Where is the crack? Where is the problem? Another trick of time reversal technique is localization of the source of some crack or of the source of some acoustic emission. And it's easy to localize by time reversal, so-called burst acoustic emission. Burst acoustic emission means that we can see one isolated acoustic emission. It was like the signals on the second slide, I think. But in case of continuous acoustic emission, that means, for example, a leakage of some gas from pipelines is a continuous signal, and it's not so easy to localize it by TR. but we find out that we are able to do it, but we have to use not only time memorization, but also cross-correlation. So there are several steps to measure it. We have source, some continuous source, we measure the signals, we send back these signals to the roughly estimated position of the acoustic emission source, and then we have to calculate cross-correlation function between obtained signals. And after the cross-correlation, we can see that it works. And we can see that we obtain the localization of the acoustic emission, and it's clearly localized. But if we don't use the cross-correlation function, if we use only time reversation, we obtain something like this. And we cannot see where is the crack, where is the, no, not crack, where is the leakage, the point of the leakage of the gas from pipelines, for example. So this is the important for continuous acoustic emission. It's necessary to use time reversal and also cross-correlation between obtained signals. And at the end of my presentation, I will present you the connection of the classification of TR signals and phi divergence. We measure with my colleague Sergio Santos at the University of Tours some signals which coming from the water tank. We have a capillary here, and we have an emitter, transducer, and here was the capillary, and we measure two types of bubbles, big bubbles and small bubbles, because we had two types of capillary, and also we measure the flowing of ultrasound contrast agent in the capillary. It's different from the previous experiments because it was done at the university as a biomedical application of our classification method. And here's the scheme of the experiment. You can see emitter, transducers. Here is the source of bubbles or ultrasound contrast agent. And the process of the experiment works as follows, is on the scheme. From the emitter, we send a chirp signal, that means something like this. We use positive or negative chirps, and we send it to the system, and we measure the response of the system to this chirp, and we measure the response if there were some bubbles or if there are no bubbles, and we after receiving the signals, we did a cross correlation of this response with the chirp, with the source chirp, and then we time reverse the signal and send again from the emitter to the system, and we measure the response of the system. And these measured signals were then used for classification. And here we have an example of standard signal parameters like RMS, rise time, skewness, kurtosis. These are standard parameters. But you can see that in this experiment they don't work very well. You can see that clusters are overlaid, that we are not able to distinguish the groups. So we were thinking how to do it, how to distinguish between small bubbles, big bubbles, ultrasound contrast agent. So I tried to apply our phi divergence, and voila, it works. We can see nice clusters. Not here, but here we can see distinguish it only from this figure we are able to distinguish between clusters. So it can be supposed that for almost every classification method, it will be easy to find a cluster. For example, fuzzy classification can work very well on this easy classification task. And we also try to classify small bubbles in different positions. That means that we move the source of the bubbles in the water tank and we try to classify the position of the small bubbles. In this case, fuzzy classification was not so good because it classified these two outliers like one cluster and put these two together. That's why that was the reason why we try to apply again divergence-based method, our divergence decision tree on this data set, and we can see that in this case the method is able to distinguish that here are two clusters. So again, divergence works very well in classification in our application in parameters and also like a classification method. And the result of this experiment was published last year in the Journal of Acoustic American Society. So it was a good result for us. So, conclusion. What I talk about, that phi divergence works very well as a parameter for signal comparison. We can compare the whole spectrum, not only one value in the spectrum, but we can compare whole spectra, and so we take into account the spectral frequencies with small amplitudes, not only with the big amplitudes, and this is the advantage of this parameter. And we have a wide range of divergence families, and so we have a possibility to choose which divergence is good for the application, and we can also tune some parameters of phi divergence. And I showed that the robustness is for us also very important, and I showed that we proved that Hamilton divergence is data robust, and this is important for application. And phi divergence works also very well as a part of classification method, and it was demonstrated that it has better classification capability in divergence algorithms. So thank you for your attention, and if you have any question, please ask me, but I am a little bit nervous, that's why I have this joke here, but you can ask me and I will do my very best to answer them, or you can, if you are interested in signal processing and or in application of the phi divergence in material science, you can also contact me, or if you plan to visit Prague, you can contact me also, and I will do your guide.
Okay, thank you very much. So, Zuzana, what you say is what you have said. So, somebody wants to formulate a question?
No.
And nobody formulate questions? Well, I always do the questions.
Yeah.
Look, I am very interested in knowing a little bit how did you construct the data file to make the statistical analysis? Because in the examples that you showed to us, you put sensors in to obtain, you know, the acoustic emission, the acoustic signals. And at the beginning, you show us some what happens with the signal, with a figure. But then you put it some parameters to simplify the signal, because the signal, and one of those parameters were applied to the phi divergence. You apply the phi divergence as a parameter on one of these parametrizations. In the first one, as far as I remember. So there was a formula with, I don't know, you put it as a finite number of values divided by 2. But this means that when you calculate the phi divergence parameters, somehow you are doing a categorizations and the phi divergence is assumed instead of, let's say, integral between.
Because we digitalize signals.
You do a categorizations and you are working with phi divergence as assumes. Assumes.
Okay. Because our spectrum is not continuous, because you measure digitalized signals. So you have the vector. So it has, I don't know, for example, 200,000 values. It's a spectrum. These values are a spectrum.
Yes, and you constructed something that sum up to 1.
I divided all of values by the sum of all, in order to have something like spectral density. Because after that I want to apply phi divergence, and I need something like probability measure or something like this. That is the reason to normalization, and it works. It's not fault to divide it all values by the same number. It works. It's only about amplitude, but still you have there information about where is the maximal amplitude. This information is still inside this normalized spectrum, and you can compare by means of the phi divergence the spectra as a whole, and this is the big advantage of the phi divergence. You obtain the one value, but you got the result of phi divergence is one value, but you compare the spectrum as a whole, and this is the advantage, because standard parameters and signal processing try to only find what is the position of the maximal amplitude, what is the value of the maximum amplitude, and this information, it's good, but it's not enough, because sometimes you have more information about the signals in the smaller amplitude and the frequency with small amplitude, and the phi divergence works with these values. So this is the advantage.
So at the end, each of these let's say signals that looks like a function. In fact, they are vectors, and when you calculate the phi divergences, you are calculating the distance of those vectors that are in fact transformed to probability distribution, in the sense that the components are positive and sum up to 1. And then when you continue, you also show us that the family of phi divergence is huge family, because you can select 5, the function phi, and you show that some phi divergence are robust and with different properties of robustness. So you were looking for subfamilies or the family of phi divergence with good properties from the point of view of robustness. But here we are speaking about robustness of the distance, of the pseudo distance. And And finally, you selected one. In what you have presented to us, not only an experiment in the first part of the talk, but you use it also 5 divergences in the second part. Were you using the same family of 5 divergences when you use for classification? That the one you used at the beginning?
Yeah, it was the same. Before all, I used Hellinger 5 divergence, but Hellinger. But at the beginning of my research, I started with comparison of different types of 5 divergence, and I find out that there are only small differences between the values and the capability to work well in classification, and the Hellinger was the best. So that's why I use it for calculation of the signal parameters, and it was during online experiments it was the same. I prefer this divergence, but it's possible to apply another divergence. But okay, it's another part of my investigation. But for practice, we can see that there are only small changes between the types of divergence when you use Hellinger or like Amherst.
So concerning applications, you are working in detecting, let's say, small breaks or shocks in the structures. So these are tests, non-invasive tests that do not destroy, but also to detect points where the acoustic emissions is flooding, like or maybe where gas is going out of the pipe, or well, this looks very interesting. So going ahead in the future, you are now using this kind of tree classification trees. Well, what is the next step? Going ahead to put it classification trees in forest, in London forest. What was the idea?
It's possible also to use the tree in the forest, but now my colleague Milan Klada at this institute works on some neural networks, and it's really popular in this time. So maybe we will change a little bit the classification method, and we will compare our standard method with neural network. But for neural network, we need a lot of signals, a lot of measuring, and it's also time consuming. And the standard method works not better, but it's easier to use it if you have only few measuring, and it works. I think it works quite well. But now, in every branch it's popular to use neural networks. So we work also on it, and my work is now to prepare some good signal parameters. So this is my plan in future to work more with phi divergence as a signal parameter. How to use phi divergence as a signal parameters or in signal parameters. We can measure another types of signal parameters and then use in some sense phi divergence between these measured parameters. And this is my work for future, because after this, if I will have lots of parameters, we can put it into some neural network and we can classify very well. So for this data set, I had only a few measurements. So It's not necessary to apply neural network if you have 100 measures, 100 measuring of the signals. But in future, we will use neural network in connection with phi divergences as a signal.
Okay, thank you. Any question more? So thank you very much, Zuzana.